Hello, everyone. Hope I'm audible to you. So, we'll begin today's session. And before I start, This meeting, it's showing that it is being scheduled for 1 hour. So I think after 1 hour, it might automatically get disconnected. So in that case, I'll be putting a meeting code link for a second meeting before it gets over, and you can join in that. Uh, Last time this didn't happen, again it's showing to me, so that's why I just informed you. All right, so I'll just share the screen and just let me know if it's not visible or not. I hope it is visible to you.
Yes, ma'am.
Okay, so welcome to yet another problem solving session for the course Geographic Information Systems. The course instructor is Professor A.K. Saraf from IIT Roorkee, and I'm the teaching assistant Anshana from IIT Kanpur. So this today we'll be discussing the week five lectures or the topics that was discussed in week five, and we'll just go through few of the problems also related to that. So we'll be focusing on the GIS analysis part today. I'm sure you might have already gone through the lectures, but then we'll just have a recap of what all topics were discussed, just to refresh your memory. So this was already discussed in the previous session as well as in the previous week four lecture. So the GIS analytical operations include these primary operations that are like area and distance measurements, buffer generation, reclassification, etc. So these are certain things that we use in order to analyze the uh, GIS database, like data set that you have, and data we normally get it from the GIS database. Now earlier we like now we have a very what do you say, very robust database available for different requirements. Earlier, the user had to find these like the person who's doing the analysis had to figure out getting the data and everything. But now, more or less, we have compiled data sets available which can be used for the GIS analysis purpose. So the analysis operations include these following. So we have the data selection or query or retrieval. Then we have the reclassification. We have the overlaying operations. We have the region transformation or measurement. We have the neighborhood operations. We have the connectivity operations. So we'll be discussing one of like each of these a little bit in detail, not as detailed as you've seen in the lecture. So I'm just recapping the topics. If there is anything that you need to know specifically, you can ask me in between. I don't want it to be a complete repetition. That's fine. So before we go to this data selection and retrieval, so you are aware that we have mainly two types of data, right? Spatial data and non-spatial data. So spatial data, we have this vector data, raster data, TIN, and in non-spatial or attribute data, we have different segregations like nominal data, such, all those things. So in a case of spatial analysis, like you have a spatial data and you're doing the spatial analysis, it involves both the attribute and spatial queries. Okay, so what is this attribute query or what is this spatial query? So just a minute, let me just get my pen. Okay, so as I was saying, we have the attribute query, and then we also have the spatial query. Okay. So in case of the attribute query, so what exactly it involves is it involves the processing of the attribute or the non-spatial data. So as the name suggests, it has something to do with the attribute or the non-spatial data. Okay. So this is independent of the spatial information, as the name suggests. So it's non-spatial. So you don't have any kind of location specifications. Okay. So it's more like, for instance, you have taken the India map from the database. So you can actually customize it according to your need using the attribute table. So for instance, if in the map that you have downloaded, you have all these district information, you have the state information, boundary information, all those things. And you don't need it that elaborately, you just need the state boundary information. In that case, you can just disable the district boundary attribute option. So accordingly, you can just use the remaining data that you require. So attribute query involves the processing of the attribute or non-spatial data, which is independent of the spatial information. It doesn't have anything to do with the, uh, the coordinates or anything, location for that matter. But in case of spatial query, it involves selecting the features based on their location. Like that's what I'm saying. It's directly, related to the name that it's being given. Attribute or non-spatial means it doesn't have anything to do with the location. Spatial query has something to do with the location. So location or the spatial relationships, one with respect to the other, such things. So here, for instance, like you have a map and you have a road that is passing. So when you give the spatial query, like you need to know certain information which is within like around maybe say 200 or 500 meter around this road. So that kind of specification you have to give with respect to the location. So that is what a spatial query does. Attribute query does not do that. It just is more a generic kind of thing. Like it doesn't have anything to do with the location. It's more or less based on the information that is available in the attribute table. So in case of data selection and retrieval, that is the first one, okay? So here we have data selection or query or retrieval. So in case of data selection and retrieval, data retrieval involves the selective search, manipulation and output of data without the requirement to modify the geographic location of the features involved. So what actually we do is we are selective. This is very important. We are selectively searching, we are manipulating the data a little bit, and basically we are not modifying the location as such, but then certain modifications in terms of maybe you are given 100, hmm, let's say you have uh, a box with 100 balls or something, and you like different colored balls, and you're just requiring red colored balls. So that is selective search. You're just taking the red colored ones. And if in certain data you require slight manipulation and output of the data without altering the geographic location per se, then that is what you do in data retrieval. So whenever the data is out or whenever the selection is done, we have to be careful to understand that if that selection is actually right. Like you have, since it's based on the person who is doing this, the decision of the person who is doing this data retrieval. So you have to be very careful that you have selected the or made the right selection, or if you have done something wrong with that query. So both in spatial and attribute data, we can do this data selection or retrieval. And one important point that you have to do with in case of spatial query or attribute query is that like you have to remember is that no changes are made in our data or in the like anything related to the geographic location. Like data is not completely altered. Like certain selection and certain manipulation is the only thing that is being done. So, like, if the area or length is measured, like, let's say you have 2 points. Okay, one point is here, another point is here. You want to measure the length or distance between these 2 points. Or, so in that case, a new field can be generated in the attribute database. Like, if you have used any of the GIS softwares and if you have seen the attribute table, so it will have so many, information given here. So if you are measuring the distance between 2 points in a particular map or something, then that can be included in this attribute table, and that distance parameter will also be included here based on the spatial or attribute query that you've done. And there are certain map calculators available with different operations. In some of these, not some, just some of these, or almost all of them, it has certain map calculators available. Like for instance, you can give some conditions in like in these calculators and all. You can just say like for instance, if this particular area is larger than this, then we need that in the map or something like that. Give some conditions. So such operations can be done using map calculators, which are available in the GIS softwares. So here, this is one example that was given by the professor. So here you have three layers that have been overlain like this. So here we need the information of this particular pixel. Okay, this particular pixel belongs to the sixth row. So that's like one, two, three, four, five, six. Sixth row, seventh column. So one, two, three, four, five, six, seven. Seventh column, and its value is 2. Because what is it? It is silt. Okay, so that much information is there. Its XY information is there. And then in map 1, like it is giving you information about the soil. So what kind of soil is it? So soil is silt, and probably the thickness information is also available. So that will be given. So the thing is, in case of data selection and retrieval, you have so many, small grids over here, right? The pixels are here. But you just need the pixel information for this particular square. So instead of trying to find each and everything, you are basically selecting this particular one, and then you get the information in all the three maps. So map 1, you got the information that the soil is silt and its thickness is 5. Map 2, you got the information regarding the rock, that the rock is granite and its strength is really high. And in map 3, it is talking about the slope. So slope is gentle. So this way, like here you have a huge data set if you think about it. Like in the first map, you are getting the soil information, and in that itself, you have to understand between the sand, silt, and clay. And then you have the rock information, then you have the slope information. So that is like huge amount of information that is available, and you don't need that much of like you just need information about this particular area. So you do the data retrieval, or like basically you select and retrieve the data for that particular set. That is the gist of this example that is being given. Then moving on to the reclassification topic. So reclassification, it's basically the purpose of reclassification is to reduce the number of classes from the original map. So as I said, here you have, let's say you have a map over here, and it has like sand, silt, clay, that much of information. Or you can just imagine that you have a single map, okay? A single map which is considering, which has all these information. So instead of three different maps, let's say you have a single map which contains information about the soil, it contains information about the rock, it contains information about the slope. Now let's say somebody who is in the agricultural field needs to know just the soil information. They don't have anything to do with the rock information or the slope information, but you just have the single map, right? So in that case, you do the reclassification. So reclassification basically involves the selection and presentation of a selected layer of data based on the classes or values of a specific attribute. Okay, it involves looking at an attribute or a series of attributes for a single data layer and classifying the data layer based on the range of values of the attribute. You don't have to complicate it as much. The only thing you have to keep in mind is the purpose of reclassification, or just this sir has also mentioned it. I'm just putting it here in simple terms. So the purpose of reclassification is to reduce the number of classes from original map. So in as the example that I said, so you let's say the classes where you had three classes. Okay, this I'm just giving a random example because we had just discussed an example like that. So you have the rock information, you have the slope information. These are the classes that are available, but then you don't need these many information like your user defined, right? So for the analysis purpose, you just need the soil information. So instead of three, you tone it down to one. Okay, so here we had three, you brought it down to one. Even here they've given the example that reclassify a soil map into a pH map. So in this case, you have a soil map, and then you incorporate the pH information, and then you classify it based on the pH instead of just the soil. Or you can even classify an elevation map into classes with intervals of 50 meter. Like for instance, digital elevation models, they have a lot of information available, right? Regarding the slope, the elevations, the valleys, mountains, peaks, everything it is there. But instead of just looking at it in a wholesome manner, if you have to just look at the elevation in terms of like 50-meter slope, then you can just classify it accordingly. So then it will become intervals of 50 means like let's say 0 to 50 meter and 50 to 100 and 100 and 100 to 150. So it goes on until there. Okay. So these classifications that we were talking about, they can be based on the number of classes that are formed before and after the classification. We can have three types. Okay, so this is how, based on the number of classes before and after the classification. So this you have to keep in mind before and after the classification. How many number of classes are there? Depending on that, we have basically categorized it into three. So we have the one-to-one classification, then we have the many-to-one classification, and then you have the one-to-many classification. And this name itself is pretty straightforward when you think about the definition. So it's basically one-to-one is when you have the number of classes before. So I'll just write it here. Let's say number of classes before, we'll denote it as B, and the number of classes after, we'll denote it as A. Okay. So when the number of classes before is equal to the number of classes after the classification, we call it as one to one. So B equal to A. So in this one, there is no change in the geometry of the spatial objects. It's just probably just reassigned, like the name or something, just slightly changes there, but the classes are more or less same. Like you don't have any reduction in the number of classes or any increase in the number of classes. Then when you come to many to one, so many to one is when the number of classes before is before is greater than the number of classes after. So B is greater than A. Everything you just remember like this, before, after. So before and after, if it is equal, we call it as one-to-one classification. If the number of classes before is greater than the number of classes after, we call it as many to one. Okay. Then we have the one to many one. So in one to many, we have the number of classes before is less than the number of classes after. Okay, so this just keep in mind that the classifications can be categorized into three based on the number of classes before and after the classification. And they are of three types: one to one, many to one, and one to many. And they're noted like this: one to one means one is to one, many to one is m is to one to many is one is to m. And then here for ease of understanding, I have denoted it like this. But the only thing you have to remember is one to one is when the number of classes before is equal to number of classes after. Many to one, many. So you remember something is greater. And then we are always keeping the before number of classes before in the beginning. So that is before, after. We'll always be writing it like this. Then just look at the name. So one to one. Okay, so best way to remember it. It might be easy for you. I'm just giving you a tip so that you remember it easily for your exams if they ask. So you just write like this. Now one to one. So it is equal. Okay. Now many to one. So always remember the first one is always this one. Okay, before one. So many means something is greater. So B greater than A. Like the number of classes were before is greater than number of classes after. Then one to many. So B is one and then just to many. So this is like this. So this is an easy way to remember the different categories of classifications available. So here we have the example. So this is a vector data example, like it's a polygon map. So you can see here, right? Different polygons are there, and you have different classes also, like different rocks which are available in this area that has been mapped, and that has been given as abbreviations over here also. I'm not pretty sure what each of them are, but then yeah, this is the case. Like the rocks have been classified over here. So, for instance, like right now, you just have a map which has classified the different rock units that are present in this area. Now, suppose your attribute table has information, some other information, additional information present, then I can basically reclassify this map. Okay. So, you need to have that information available, only then you can do the reclassification. Okay. So what we can find after the reclassification is this. So the same map over here, you can see the shape and everything. So the same map, but in here we classified it into 7 classes based on geological age. So here you can see how many classes are there. One, two, let me just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 times 2 around, so it might be like 32, I guess. So here we had 32. But then when you reclassified it based on the geological age, you only had 7 classes. See, it got down to 7. Here you brought it down to the classification to the geological age. Now, when you again reclassified it based on the type of lithology, like whether it is an igneous rock, whether it is a metamorphic rock or sedimentary, it became even broader. So here you only have 3 classes. So you can see if you go from here to the previous one, then you can see here only 3 were there. So like you have a red color, blue color and a green color. That's all. Nothing more is there. This is something regarding the general lithology of the area. Then it was classified based on the geological age. So 7 classes appeared. Even then, it doesn't seem that complicated or anything. You don't have that much of information, or like too much of information over here. But in the previous map, you can see how many classes have been formed. 32 classes based on the rocks that are present here. based on the mineralogy of the rocks or something. So that is this is one really good use of reclassifying a map, a geological map. Or like here we have used the example of geological map, but then you can also try it with other sort of maps. But only thing is you need the other information like the geological age or the lithology information available in the map, like attribute uh, table. Then you can just use that and put it here and for reclassification. So it becomes very less complicated. So a person who is studying the probably I think this might be the mineralogy. I'm not very sure. But if suppose it was a like classification based on the mineralogy of the rocks or something or the rock specific rock types, then somebody who is studying that area in that much detail might require this map. But somebody who is just looking at the age aspect just requires this. They don't need this. Then there is no point in keeping this one, right? So they will reclassify the same map in this way. And somebody who just needs to know the lithology, they have to just use this one. So it's all based on the user. From the beginning of this course discussion, that is what we have been implying. Like GIS has so many features available. So what kind of analysis do you do, or what kind of modeling or model you end up with, is based on what the user needs and nothing else. So here again, you are reclassifying a map with the attribute data. So it's a slightly different example, of course, like not the like the other previous one. So we are basically reclassifying based on the attribute information. So here we are having the land use information available. Okay, if you take a look at this, the commercial use, the industrial, institutional, recreational, residential, and water. So in that way, this attribute map has been land use map has been generated. So basically, the city blocks are here. So you have this over here. And then you have a attribute table giving you information regarding the land use of each of the block. So you combine both of this and you make it like this. So the reclassification has been done accordingly. So this is kind of an example of one-to-one classification. So here you have not added any more what do you say, classes, or you have not reduced any more classes. You have just merged these two. That's all. Like the city blocks number has not changed, right? And you just added this land use information. So that's the only thing that has been done. So it's like example of the one-to-one classification. So here basically no polygons have been merged or no new boundary has been generated or any of the polygons. And like the previous example, in the previous example, there was merging of data because you had initially 32 around classes and then you, for one map, it was brought down to 7. For the other map, it was brought down to 3. But here, none of that has happened. Then we have another example of data reclassification. This is reassignment based on the attribute value. So here, the example that you have here, you again have a soil map. So it has been classified into 1, 2, 3. So one is alphisol. This is like type of soil. Okay. So alphisol is there, mollisol is there, and red xena is there. Okay. And the other information that we have here is the infiltration, like how water can infiltrate in these particular soil types. So we have the infiltration values that are available, and this like initially this has only been classified based on the type. Now you have the infiltration values available. So you can just reassign this and you have a infiltration map available over here. So if two adjacent areas are having the same infiltration value, then they are appearing as one single polygon. So here you can see alphazole and mollisol. Molisol has same infiltration value as 3030. So when you reclassify this, you have just two classes available because alphazole and molisol have the same infiltration number given here. So what you have to keep in mind is in the system, you have information for each and every cell. Okay. Only when you're reclassifying according to your requirement, they merge. But when they merge, that doesn't mean that the information is lost for any of the cells. The information is still there, but only thing is you are actually incorporating some selection criteria into it or reclassification criteria into it, which sort of sometimes merge it or sometimes brings in more classes. Okay, you can just keep in mind all these examples of data reclassification because for those of you who are working with especially like land use, land cover data set or something like this would be very helpful. Not just for LULC, but for other purpose also. Like just now we have seen for the geological map or whatever. It's always based on the user requirement. Then we have another one. So here the reassignment is based on attribute name. Okay, so the new map should only have reclassification is done that in order to generate a new map, if the soil map equals to red xena, like we are only focusing on this one. We had alphazole, we had molisol, but the new map, according to our requirement, or I'm asking like I'm giving the information in such a way that only in order to generate a map which contains information only about red xena. Okay, so if the soil map is equal to red, like if it is true, like wherever that red xena area is there, we denote it as 3. And wherever it is false, like it's not red xena, we denote it as 0. So here, this green one is red xena, right? And here we have the red as molisol, I mean alphazole, and the pink one is molisol. So this is a conditional operation because we are only looking at the red xena part. Okay. So here you can see wherever molisol and alphazole was there, the value is given 0 because it's not red xena. But where you have red xena, it is given as 3. So this is another type of classification that can be done. So it's always based on the user requirement. Okay. And as I said, just because we generated this new map doesn't mean that we lost all the information regarding molisol and alphazole. That's not the case. We do have that information, but in this new map, we don't need it. So we just removed it. That's all. So here you can see we are doing it sort of in stages kind of thing. So one, two, three. First you had that. Then we incorporated this 30, 25, the infiltration map. And then later on, if you need a specific soil type, then we included just that one. That's it. This is another example. So here you can see that uh, instead of having a continuous digital elevation model or continuous values, uh, we are just dividing it into three classes. So here you can see it's kind of like a gradient. You might have seen that option of coloring certain blocks or something. And if you have used the Illustrator or just in PowerPoint presentation, you have seen this gradient thing, right? So in this DEM, it is more or less, it's very continuous in nature. Okay. You can actually pinpoint where this red is getting over or where this dark green is getting over or where it's not very clear. You just know some demarcation is there. That's all. But here the reclassification is done. in order to obtain those three classes separately. Because here you have a gradient from 0 to 900, that's it. But when you reclassify it, you are telling the you are giving this information or input that I want to classify this based on like say in three classes, and class 1 will be from 0 to 200, class 2 will be from 200 to 400, and class 3 will be from 400 to 900. So accordingly, you can see how it has been classified. This is the DEM image, and then DEM has been classified into this format. This is for ease of understanding. Okay. Sometimes you just need to know this, maybe this just this information. You don't need this gradient information. So you can do this. So this is kind also known as slicing because we have sliced it into three classes. Then yeah, then it brings us to logical functions. So you might have learned, those who have taken this not taken, but if you have studied your mathematics, you might have studied about sets, right? So you know this intersection, union, all those things. You might have learned it in your 12th grade or 11th grade, I think. So the similar idea is being input over here in case of Boolean operators. So in here, you have to keep in mind that in GIS, we are not actually dealing with very simple data set. We are most of the time for generating a model or for big projects, you are handling a lot of data sets. So it's not very simple or straightforward. But then such functions can be done in order to make the classic like whatever analysis that you're going to do a bit more easier. So here the basic idea is almost same. So here A and B means a place where you have both A and B. So if you do it in this circle manner, so you have a circle A, then you have a circle B. So A and B means where both A and B are present. So that is the intersection. Then A or B means it can be A or it can be B, like which means both. So the entire thing will be included. A XOR B means excluding the intersection. That is exclusion, excluding OR. Okay. So the intersection is removed and you have A and B. Then A, not B means you will not at all take B and you will also remove the intersection. Like B should not even a little amount of B should be present. So these are the different Boolean operators. This you have to keep in mind. Okay. You might already be familiar with this. You might already know this, but then it's better you just keep this in mind because I've seen in the assignment also. I think a image was given and then probably they've asked about this. That's why I mentioned it. So these logical functions, like we call them as logical functions. So these can be performed not only on the vector data, but it can also be done with the raster data. So like in case of vector data, like if you have especially polygons, not like point or lines, but especially in case of polygons, you can perform, but then more, you can also do it in lines and points also. But mainly, evidently, you can do it in case of polygons. In raster, it's actually I think I said the opposite. Polygon, it is actually a little bit difficult when it comes to vector data. But it's might be like basically vector data. It's a little difficult to deal with when you do the logical functions. But in raster data, like if it's not much of an issue, if it is very well georeferenced, then you can easily apply these logical functions in that. Okay, so I'm getting the prompt that this call will end in 15 minutes. So I will put the. Mhm. link for the next meeting. Like as soon as this ends, I will log in from that. So I'll put it here in the chat. Just give me a second. Let me just make it and I'll put it here. All right, so I have put the meeting link for the next session because the thing is, I don't know, it only happens occasionally. Last last time I could take 2 hours at a stretch, but this time it's showing like this. So I put the meeting link. You can join in that. Okay, so where will we? Yeah. So overlaying operations. So that is the next type of the analytic the functions that you do. GIS analytical functions. So here it involves the integration of multiple data layers. The name itself suggests, right? You're overlaying something one over the other. Excuse me, just a minute. So here we have multiple layers and we can use it in combination. Also, we can even combine the vector and raster layers also together. Okay, so we can basically perform the overlaying operations in all of these things. So here, in this example itself, you can see, right? You have different information over here. I think this might be the wells available. Then you have the water system that is there. Then you have the building information. I think the underlying lithology probably. Soil type. Yeah, soil type is there. Building owner is there. The well type and the location, everything is there. And then you just combine everything and one single map you have. So it's like overlaying the information. So both vector and raster data can be combined together. So in the concept of overlay, here you can see map overlay basically. So this is one very simple example. It's not as simple because in reality you might be dealing with very complex data set, but this is something for a better understanding. So here on top, here we have one map which is belonging to the same geographic extent and it has two polygons as A and B. Now for the same area, there is no difference in the area. So for the same area, we have another polygon map which has two units, 1 and 2. It's different, right? A and B is different, 1 and 2 is different, but the area is same. Now, when these, you can see that these polygons 1 and 2, it's completely different from the size and everything, shape of the polygon A and B. Now, when you intersect these two, okay, what will be the output that you're getting? And you can see it over here. We have basically 4 polygons because you're including this. So instead of like you have 2 here, 2 here, but in the output you have 4. So instead of, let's say, if you have 10 polygons here, like sir has also given this example. So instead of 2, let's complicate it a little bit. So if it is 10, like A, B, C, D, like that, you have 10 polygons over here, 10 polygons over here, then you may even end up with 100 polygons in the output, depending on the shape also. But it's not necessary that you get 100, but then equivalent to that much you can get. It's a possibility when you do the overlay. So then it becomes a little complicated. Then you can even do the reclassification if you feel that it is too complicated and you don't need that much of information. So that can also be done. So overlaying is basically combining everything. Reclassification is basically sort of like segregating the information. Then you have another one like vector overlay using polygons. So you have map A, which has just 2 units. So here you have 2 units. Then you have map B, which is having 4 units. Now, when you intersect these two, like map A and map B, so here you have A1, A2, B1, B2, B3, B4. So when you intersect these two, you can see the result like this. So instead of 2 and 4, here you have 1, 2, 3, 4, 5, 6, 6 units in the map C, which is a combination of A and B. And here a new topology would be constructed, and that topology which will have extra tabular data, extra field data. Like for instance, here you have this C uh, has been divided into C1, C2, C3 like that. And for each of the like C subclasses, you have A and B subclasses also. So if you take the C1, C1 has information of A1 and P1. C4, if you take, C4 has information of A1 because that is including that part. And then in terms of B, it has information of B2. If you take C3, it has information of B3 and A2. So here you can see. So A1, in case of A, the subclasses are A1 and A2. And in case of B, it is B1, B2, B3, B4. So, and then C has 6. So accordingly, you have a new topology that has been constructed. Then here you have the vector overlay examples like impose, stamp, join, and compare. So here a lot of possibilities are there. Like impose is basically intersecting. Here you can see you have a circle, you have a square. And then when you intersected it, those regions which are going to stay out of this circle has been removed. So you have components of map B, but then it's not complete. So you just, you know, kept the circle. It's not a very good circle, I'm sorry. But then yeah, this is the idea. So this part has been removed, which is staying out of the circle. So this is the idea of impose, like means map A and map B is here, and output is a combination of both A and B. This is like you can as easily say it is intersect only, but then as sir has also mentioned, in certain softwares they use this term. So it's better that you are familiar with such terms and not get confused. Why like where you are aware of the concept of intersection, but then you don't know how like you don't have any idea about impose. So in that sense, it's better that you keep this in mind. Then you have this stamp over here. So that is like combining these two, a union is created. So here you have 1 and 2, 1, 2, 3, 4. So you just combined it and then you have another like it's basically 1, 2, 3, 4 are there and then you just put it on top of this. So we have another 5 and 6, a new set that has been included. In case of join, again you're joining it like 1, 2, 3, 4, but then this 1 and 2 they have considered unlike here um, here for 1 and 2 they have actually after stamp option was done it became 5 and 6 instead of joining with 1 and 2, but here it is joining with 1 and 2. That's why we have a shape like this 1 and 2 and this 1 and 2. Okay, then we have comparing, that is A and B. So one, two, three, four, and then like this. So you compare, and wherever the common parameters are there, only those we are taking. So one, two, three. Just familiarize yourself with these terms, that's all. Because this is mainly like the terms that you use, like intersect, union, not, exclusion. It's essentially that thing. But then, as Sir has also said, in certain softwares, they use it like impose, scan, join, and compare. So for such purpose only, we have just mentioned it here. Bringing us to the next one, like next feature available, that is like clip or extract. So we can also call it as extract in softwares like ArcGIS. So this is basically retrieving the data on based on the polygon boundary. So here you have this point data that is available. Okay. In this case, you have the point data. This is the example that you have uh, here. You have this circles in the clip coverage. So the output coverage is basically anything which is within this clip coverage. So in a clip coverage, if you just superimpose over here, only 2 and 3 are coming. Okay, so when you extract, this is the input, this is the clip. So when you extract, only this portion will come out. So these 2 points will only come here instead of 1, 4, and 5. This is for point option. Okay, then you have the line option. So here the input coverage has polylines like 1, 2, 3, 4. Like these are the points, and then you have polylines. Okay. And clip coverage is the same as in case of the point thing. Like same thing you are using here. So again, whatever is going to be there within this clip coverage, only that will be extracted. So the output coverage will only have that. Okay. Same thing you are doing here also in case of poly option. So the clip coverage you are using the same thing, but in different vector data like point data, line data, polygon data. So that is the clip or extract of ArcGIS. So this is like a realistic example or something that I have done is like basically uh, for my research purpose when I'm, uh, I need a particular portion of the map and not the entire map. Then I use this feature. I incorporate the necessary clip like shapefile to clip the image and then I extract the image. So that way you can just, this is all like based on your requirement. My requirement was just to get that particular area from the big map. So I got it like that. So that's it. It's showing that the meeting will end in 2 minutes. So as I said, I have added the link for the next one in the chat. So you can, if you're interested, you can join in that. Then the next one that we have is erase option. So basically, it is excluding those areas which are not common. Okay. Earlier in clip, what were we doing? We were only extracting those areas which were common. But here you are removing the area which is not common. So here again, the same circles we are using here, but for erase coverage instead of clip coverage. So here 1, 2, 3, 4, 5 you have. So this much area, whatever is present, will be removed. So 2 and 3 comes in these circles. So those are removed, and instead you have just 1, 4, and 5, which are on the outside part. Okay. Then you same thing you're doing for the line option. So you can just see the difference over here, right? So line option you see. So here, if I'm not very good with this image drawing, but yeah. Okay, I'm not drawing on top of that, but I think you get the idea, right? Whichever part is out of this circle, okay, I think it will end, so I don't want to make it halfway. uh, let this meeting end, and then I will explain it when the meeting restarts again. So here, as I was saying, I think I'm audible. Yeah, anyway. So as I was saying, so in point option, line option or poly option, so basically you are giving that area which needs to be removed. So that area, whatever data is there, that point will not come. So here 2 and 3 is not coming. In case of these polylines, the center portion is not coming, the outer portion of these lines are coming, and 3 is missing because 3 is exactly coming in the center part where the erase coverage is there. Then here, if you see, wherever this circle is coming, that portion has been removed. So this is how you use the erase option. Okay. Then we have the union option. So we can have an extraction that is intersection, exclusion, or union. So union example is basically you are combining everything. So here you have like 1, 2, 3, 4, 5, and the union coverage is like this. So basically everything has been included in this. So you see, it's a like very crowded because this information is there and this information is there. So output coverage has all of that. Okay. And here the Boolean operators that we were discussing, we are using the or option here. So A or B. So you are using both information, whatever is available in A as well as in B. You're combining everything. Then we have the intersect option. So this is the AND operation, like how in the union one we were using the OR operation. So here it is the AND operation. So when the two coverages are overlaid, only portion of the input coverage that falls inside the intersect coverage will remain in the output coverage. So this is the input coverage. And only that portion which stays within this intersect coverage will come out in the output coverage. So here it's basically cutting that area. So here it is essentially, let's say you have a circle like this, okay, and I'm just simplifying it. You have a square like this. So you are using not adding, basically you're doing the AND option, okay, Boolean AND operation. So when you do the Boolean AND operation, you're basically, it's like the portion that is, it's not so rounded because wherever that uh, square is coming, that portion has been included here. And the entire circle has not been included. While the intersect coverage must be a polygon, the input coverage can be a line, polygon, or point coverage. That's not a problem. Input can be line, point, or a polygon, but then always the intersect coverage, the parameter that you're using, that should always be a polygon. If the input coverage is a line coverage, the output coverage will also be a line coverage. So here, this is basically like, as I said, if you have a map where you have a lot of information available. In the map of India, you have the state boundaries, administrative boundaries, district boundaries, everything is there. Now, for example, I just need information about, let's say, place, a specific place. Okay, let's say my like I belong to IIT Kanpur. So let's say I need just information about IIT Kanpur. So I don't need all that information that is available for the entire India map that I have downloaded. And as much as like a lot of data is there, that much space also it is going to occupy, and I don't want that. So I can use all these parameters and only extract the one that I need, and then remove the rest. Or if I want, I can keep the rest. But then yeah, that is where all these Boolean operations, all those this like logical operations comes into play. Then we have the identity. So here, everything which is located within the boundaries of the input coverage is collected in the output coverage. So here, the importance is given to the whatever is there. Like earlier, if you take a look at this outer portion, this portion, and this portion was removed from the input coverage. But in identity, that is not the case. Here, the priority is given to the input coverage and less to the not less, but then yeah, input coverage is given more importance. So in the output coverage, the boundary will be identical to that of the input coverage. Here you can see, here the boundary is not the same. It's sort of a mix, right? Because it's an intersection. So the circle parameter is also there, the square parameter is also there. But here you can see this boundary is in the form of a square, in which you have incorporated the identity coverage. So the identity procedures applies to point, line, and polygon. If the input coverage is a point feature, output coverage will also be a point coverage. Okay. So those things mainly we were discussing for the vector-based operations, like those are vector-based operation tools. Here we are going to discuss the raster-based overlay operation tools, which include arithmetic functions, relational functions. Again, you also have the logical operations over here, and you also have the conditional functions. So we'll be discussing each of these. So in raster-based operations, like like basically in the arithmetic functions, we will be using this subtraction, addition, subtraction, multiplication, and division. That is how it is represented. Plus, minus. This is for multiplication, and this is for division. So you can do all these basic operations in the raster layers. You can also perform the relational functions, which we were actually during classification also we were using, right? Less than, greater than, equal to, those things. And then we have the logical operations and or XOR not. This is the exclusive one. So in fact, you can actually combine these also. Like you can use arithmetic, relational, logical operations hand in hand. Then you have this conditional functions like if, then, and else. So these also can be used in combination. Like if you remember from that example, like if it is this particular soil type, then consider it as true. If not, then consider it as false, or like that kind of condition. So all these functions, operation tools can be used for raster data set. Whatever the output which the system will create, only requirement is that we have to understand that. That is the only thing. Like that's what I was saying. The person who is working with that has a lot of things at his discretion, at his or her discretion. They have to decide what functions needs to be used, or like basically they are using these functions based on the output they require. If they need a lot of information, they might have to overlay, like include everything. But then you don't. If that person doesn't need that much, then they can use these functions and remove the unwanted uh, parameters from the vector or raster data. So here we have an example, uh, a very simple example, uh, because we are not going to complicate it further. So here you have map A and our output map is C. So how are we generating map C? We are adding 10 to map A. So you're adding 10 here, 10 here. In each of the cells, you're adding a value of 10. So it becomes 15, 15, 12, 12, 15 like that. See, 6 became 16, 5 became 15, and 12, 10, 2 became 12. You added 10 to it. Okay. Like here, you are only using the arithmetic operations. That's why it's an example of arithmetic operations. It's very straightforward for the first one. Then, if you go to C1, map C1, you can see it is a sum of map A and B. Okay. So 5 plus 4, it is 9. Like the corresponding cells only we will take. Like if you're taking the first cell of map A, then you're taking the first cell of map B. So 5 plus 4, 9. Then if you look at the cell, it is 2 plus 8, which is 10. So likewise, okay. 6 plus 1 is 7. 2 plus 1 is 3. 6 plus 8 is 14. So you're just using this. These are all basic arithmetic operations. You're adding some value or you're just adding the values between these maps. That's it. Then in map C2, it's a little more complicated, not as direct, but then again, you are only using the arithmetic operation. So it is map A minus map B divided by map A plus map B multiplied by 100. So we can just use it for one cell and see one simple one we'll take. Okay. Okay, so we'll take this cell, okay? This this cell from here and this cell from here. So map A, it is 2 minus 1 divided by 2 plus 1 into 100. Okay, so 2 minus 1 is 1. 2 plus 1 is 3. 1 by 3 into 100. So 100 by 3 is like 33.3, something like that, right? So the value is 33. Or another example we can take is this 2 and 8. So it will be 2 minus 8 by 2 plus 8 into 100. So this is minus 6 by 10 into 100. This goes, it will be minus 60. That minus value is kept outside. So that is there. Okay. So that is how the arithmetic operations are done on different maps. Sometimes to enhance certain things or something like that. This is very straightforward example. So here we have only used the addition operator. Here you have used the subtraction, addition, multiplication, as well as the division. That's it. Now, we will see other examples like relational functions where you use this the greater than, less than, or equal to. Okay. So here the condition for the output map is if A is greater than B. That is the condition. Okay. So if map A cell is greater than the cell in map B, then it should fall as true. And otherwise it is false. Okay. And true is 1 and false is 0. This is the condition. Like the first condition is map A should be greater than map B. And if this is true, we will denote it as 1. And if it is false, we will denote it as 0. So we'll see. The first one, if you take in case of map A, 5, and then you have 4. So 5 is obviously greater than 4. So that is 1. Okay. Now we'll take a false one. So here, yeah, this one. So 2 and 8 is there. 2 is definitely not greater than 8. So that is false. So we gave it as 0. Same thing here. 1. Oh, sorry. 5 is greater than 4. But 6 is not great. Like 6 is greater than 1. But 6 is definitely not greater than 8. So accordingly, you are giving this true or false into the output. This is known as relational functions. Then we'll be discussing about the Boolean logic or the truth table, like logical functions. So here you have the input and output for Boolean operators. One means true and zero means false. Like this is another name, okay? Truth table is another name only. It's not a new thing. Uh, so here we have the inputs from map A and B, let's say, like this is A and B. And if it is in map A, we say it as 1. And in case of B, for instance, like let me give an example, then it will be easier to understand. So if I perform this operator, that is AND or intersection operation, so 1 and A and B, so here 1 and 1, so it is true. Okay. Something is wrong with my pen. Just a minute. I don't know what happened to my pen. Maybe I don't know what happened, but yeah, we will go to the conditional functions then. So conditional functions, as I was saying, if something, else something like that, if or else. Okay, that conditions are coming. So three things are possible. Like if false, then we will, in this case, we will get the value as 0. Again, output might be binary depending on the condition and like all those things. So here in this map A, we are having um, two things. Okay, here you have F and another is no data. Like this blank one, you call it as no data or it is unidentified. You don't have any values over here. You just have F and this one. And map B, we have three classes. Okay, we have this 700 meter, 600 meter, and 400 meter. So if I take this map C, which is over here, so here the condition is if map A equal to forest, then it is true, else unidentified, like that you are going to give it. Okay. So if it is forest, you give it as 1, and if it's not, you give it as unidentified. That is what this means. If like not if IFF map A equal to forest comma 1 comma question mark. So this means that if this map A and you're generating map C, so in map C, if that grid is a forest F, then you give it as 1, If it is not, then you give it as this question mark, which means undefined. And you can see that is the same thing that has been done in map C. Wherever f is there, you gave it as 1, and wherever f is not there, we have put it as undefined. Okay. Then in map C1, the condition is here we have used this AND operation also. Okay. So what we have done is if map A equal to forest. So same condition as above, but here one more operator has come, that is the B1. So here the 700 parameter also we have included. So map A should be forest, like it should be a forest, and it should also have the 700 meter. If that is true, you give it as 1, and if it is false, it should be 0. Okay. Now you know these are the places where you have forest, and among these, where do you have the 700 meter? Okay, so that you have to, like 700 meters is all over this place. But where do you have forest? Only these cells in this part. So only those cells have been included. So that is how, like if you are classifying, sometimes in order to make things less complicated, you can do the classification step by step. Okay, so here you have done it step by step. First you did this function, so you know where these true, undefined, all those things are. Then you are incorporating the map B. So step by step, when you do, the chances of complicating things or making like things going wrong will be pretty less. Then we have the crossing operation. So here we also call that as cross table or cross operations, and here basically it is through the table and then using the cross table as attributes. Uh, we can reclassify our map as we have done in this particular case. So here you have the forest, grass, lake, land use, land cover data over here. And here you have the geology. Okay. So this information is there. This information is there. Number of pixel information is there. So in cross table, we have this forest alluvial, forest shale, grass alluvial, grass shale, and lake alluvial. So we have combined it like that. So here only two classes are there. So it's easier to classify. But then when it is combined with these, the cross table comes into action. So here, this is one random one we'll take. For example, I'm taking this cell, okay? Here you have shale. The same cell, if I go over here, it is grass. So grass and shale. That's what we have given here. So here more number of classes have come. Like here you just had 3. Here you have 2. But here, how many do you have? 1, 2, 3, 4, 5. The number of classes is increased. You are intersecting it more or less. Not intersecting, basically uh, generating more classes by putting more conditions. This is easier when instead of using two different maps, you have a single map which has information about both, like the land use information is there, geology information is also there. Then we are coming to this neighborhood operations. So here it's basically to evaluate the characteristics of an area surrounding a specific location. So you have a specific location and then the characteristics of the area surrounding this particular location. That's what we do in this neighborhood operations. So neighborhood operations involve the creation of new data based on the consideration of roving window or moving window of neighboring points about selected target locations. It's not as complicated. Only this first definition, this thing is more than enough to understand. Evaluating the characteristics of an area surrounding a specific location. It is necessary to indicate one or more target locations, the neighborhood considered around each target, and the type of function to be executed on the attributes within the neighborhood. So you have these neighborhood operations available like interpolation, the topographic functions, or the search functions. Now, last time we have already discussed this interpolation in a little bit more detail. So uh, we can just recap it so you remember and then we understand why it is considered as a neighborhood operation. So in interpolation, the procedure of estimating unknown values at unsampled sites using known values of existing observations. In simple terms, when you say, like for instance, you have the elevation data of a mountainous region. Right? It's not possible for you to go to every single point of that mountain area in order to know the elevation information. So you will select some strategic points of which you have the information about the elevation, and then you do the interpolation. So using the data from these sites, you're actually finding data for the unsampled sites, elevation information for the unsampled sites. That is what we are doing for when we are doing interpolation. So the typical examples include point interpolation, where, like as I was saying, like rainfall, spot heights, whatever it is, like those examples are there. Line interpolation, like contours. So for those purpose, this neighborhood operation can be done. So here you remember, like what is neighborhood operation? You're evaluating the characteristics of an area surrounding a specific location. So in interpolation, what we are doing, I know the like let's say I have an area like this, okay, and I have the rainfall data of this region, and let's say of this region, and maybe here and maybe here, okay. Now, if I need to know the rainfall data of let's say somewhere over here, then it is actually very close to this point, right? So surrounding this point, so I'll be interpolating using this data for this. That's it. Then we have the topographic functions. So the surface characteristics such as the slope, relief, and form of an area are referred to as topography. When you talk about topography map or whatever it is, you're actually talking about the slope, relief, and what kind of that area is. Such surface characteristics are being discussed in a when you talk about topography. So the topography of a surface can be represented in the DEM model, like digital elevation model. So Sir has also shown certain examples of this DEM, and yeah, so in that basically we have all these information like where you have the elevation, where you have the valleys, all those things. All that data is available, slope, relief, what kind of area it is. So topographic functions are used to calculate values that describe the topography of an area. As simple as that, what the name suggests. So it helps you to understand the topography of an area. So the most common transformations working with elevation data are slope, where you see the rate of change of elevation, how the elevation is changing. Because if you have traveled to certain hill stations, for example, while going in car, if you have, out of curiosity, you can once check also like this elevation thing. So you might start from let's say some 500-meter elevation. Then if you're going up, you might go at like in hill stations and all, it might be as high as 1,500 meter or even slightly more than that. So that gradual, that rate of change of elevation is what you discuss in slope. Slope increases as elevation increases. Gradient is the maximum slope that is there. So that is called the gradient. Aspect is the direction of slope with reference to the north. North is here. In which direction is the slope going? Sometimes it might be northward itself. Sometimes it might be in the northeast direction or southwest direction or proper west east like that. So it's everything based on north. So here, the topographic functions, so typical examples include the slope calculation and the aspect calculation. So here, this is a mm, degree of slope. If it is given as theta, then tan theta is equal to, this is the rise by run. Basically a mathematical function that they're using. And in order to get the percent of slope, rise by run into 100. So if the degree of slope over here is 30, then like for instance, if theta is 30, then the tan theta or tan 30 will be the this value, like how much is tan 30? I think it is 1 by root 3. I don't remember exactly, but probably that. Anyway, like that value multiplied by 100 will give you this percent of slope, which is 58. Similarly, if it is 45, tan 45 is 1. So 1 into 100 is 100. 76 means it's 375. So like that. This is how the slope calculation is done. Okay. This basically what you have to understand is in GIS, you have a lot of operations, functions available, tools available. So it's not possible to go to each and every tool, but then we can, of course, discuss the ones that are commonly used. Then other things, basically, it's up based on our requirement. As you do the project, you will learn. That's also there because with time, as I said, like how the database is building. Similarly, these functions, tools, they are also getting improved and included. So to make things more easy, so it's constantly getting updated. So here you have input of a digital elevation map over here. So you have this gradient where it shows where you have this light blue color, that is the lower thing, and then lower slope, and then high. That's it. But we want to classify it in terms of degree slope. We need a slope map basically. So what we do is when you classify it, we do it in such a way that 0 to 7, 7 to 15, 15 to like you're making it into these many classes. So 1, 2, 10. You see, here it's not that visible, but here we have done it like this. So here we actually calculate the slope. Okay, when we go for slope map calculation using neighborhood operation, especially the topographic functions that when we get a slope and here the slopes are shown in degrees. So we are doing this classification. That's that difference only I'm showing here. You have a DEM image over here where you have this gradient thing, but you need the exact boundaries. If you remember the example I showed before, something about gradient slicing. So there you had the gradient, then you basically made it into three distinct classes. Same thing you're doing here. Then we had this connectivity operations. Mhm. Yeah. So this connectivity operation, they basically estimate values by accumulating them over the area that is being traversed. Okay, connecting, basically that is what they are accumulating the values in that area where it is traversed. So to calculate the connectivity function, we need to specify the way the spatial elements are interconnected, the rules like the possibilities or the constraints that control the movement allowed along the spatial elements. Then also you need a unit of measurement. So the reason why you have to specify how they're interconnected is because as the name suggests, it's a connectivity operation, right? So this interconnected information is very much required among the spatial objects or spatial elements. And then how things move you know what are the constraints, possibilities that means the rules and that will control the movement, such things. So, for example, let's say there is like this is an example which Professor Saraf has also given. So, let's say there is a pipeline, okay, or a river system, something which is like this, okay, or even a road, some line feature you can say. So, what are the possibilities and what are the constraints that we have to provide? Okay, so in GIS, we have different software tools, and it's up to us to choose what all needs to be done. So here you can use this connectivity operation when you are working with such road pipeline connectivity, road connectivity, or some drainage connectivity, something like that. So connectivity functions can be grouped into contiguity functions, proximity functions, network functions, spread functions, and seek functions. So first one is contiguity. So I'm not going to discuss much in detail because already we don't have that much time. Mm, but yeah, contiguity basically it measures characterized spatial units that are connected. Okay, so a ground of spatial units that have one or more common characteristics and constitute a unit forms a contiguous area. It's basically, I think last session or one before that, I don't remember exactly, but we were discussing some examples where we were saying that repetitiveness is there means we can combine them, right? So it's something like that, contiguity. So common measures of contiguous are the size of the contiguous area and the shortest and longest straight line distance across the area. Then yeah, proximity functions they involve the measurement. Unit can be distance, length, travel distance in term. Like proximity essentially tells you how close or how far something is there. Contiguity is mainly continuity kind of thing. Proximity is the distance aspect. Then you have like so in that you'll be calculating the distance and all those things. You're doing the proximity analysis and stuff. Then you have the network functions, how well connected they are. Then you have the spread functions, evaluate the spread of that particular feature, like for example, this road or pipeline that I was saying. So it's all specified to what kind of thing you are dealing with and like what you have to do with that. Okay, so it's already like we have around maybe 15 minutes more. So we'll go to the problems then. I don't have that many questions today. I didn't have like I only included those questions which are not very common in the assignments that are given to you. But apparently, last time one of you was telling me that the questions I'm discussing and the questions that it's given to you is different. So I'm sorry I didn't include it today. Maybe I'll include the week 5 questions that I have in the next session. Like we'll discuss that also. So today I only included those ones which are not very common that I saw from this year's and previous years. So yeah, this is the first question. Which overlay operation has been applied in the following feature? You have clip, extract, intersect, all of the above. You can give me the answer in the chat. I will check that. So you have this input and the output. You can see you have, I think it's a rectangle, not a square, I guess. I don't know. Yeah, anyway, that is there and then a circle is there. And you can see how the output has come. Answer is all of the above. Here you have clipped, you have extracted, and basically you can see it is the intersection that is there. Here you can see, right? This much portion is removed this much portion is removed. Whatever is common to these two input units, that has come out. So it has been clipped, extracted, as well as intersected. Which vector feature can have a centroid? We know that the vector feature include point, line, and polygon. So out of these, of course, polyline, line. So out of these, which can have a centroid? The answer is polygon. Polygon can have a centroid, not a point or polyline. So if you have a polygon like this, okay, that's not a very good polygon, but anyway, so centroid can be somewhere like this. Like that feature is therefore polygon, not point or polygon. Neighborhood operations involve the creation of new data based on the consideration of, this, in the definition itself, it was given roving into moving. If we go back, you can see. Yeah. Neighborhood operations involve the creation of new data based on the consideration of roving window or moving window of neighboring points about selected target locations. Yeah. The surface characteristics such as slope, relief, and form of an area are referred to as, we just discussed it. Yes, the answer is, so it's topography. The following figure depicts, okay, I have not discussed buffer analysis, but then if you have gone through it, maybe you can try. This is attribute based buffer analysis. I have not discussed it. Maybe if you want me to, I can discuss it in the next session. I didn't want to uh, like discuss so much of theory. That's why I didn't include it. Let's see, like if it's repeating again in the upcoming week discussion, then I'll include that in this and that. Okay, so that's all the question I have included today, but maybe in the next discussion, if you want me to, I can include the week 5, the ones this for which the solution has been released. Maybe I'll discuss that in the on Tuesday's session. So that is all for today. Uh, shall I stop presenting?
Yep.
Okay, thank you so much.
Yep. Thank you, ma'am.
Uh, I'm not able to hear. 1 second. I think. Am I audible to you?
Yeah, yes, ma'am. You're audible.
Ah, okay, okay. I'm really sorry because in between my headset got connected. So I was under the impression
Okay,
that
okay.
my speaker was connected. Okay. Okay,
Yeah,
so
yeah.
thank
Thank you,
you.
ma'am, for the
Yeah,
wonderful session. Thank you so
okay.
much.
Okay. Thank you so much for listening. And as I
Yep, yep.
said, see, I cannot discuss every bit of the theory. So if at all you want me to specifically discuss anything, you can let me know. Okay. I was just
Sure,
summarizing
sure.
everything. Yeah.
Yeah. Thank
Okay.
you.
Okay. Thank you so much.